In November 2025, China's J-20 Mighty Dragon stealth fighter made a spectacular appearance at the Zhuhai Airshow, China's premier aviation showcase where the latest military hardware is displayed to international audiences and potential customers. Over 300 J-20 aircraft have been produced, making it one of the largest fifth-generation fighter fleets outside the United States. Chinese state media portrays the J-20 as proof that China has joined the exclusive club of nations capable of building advanced stealth fighters comparable to America's F-22 Raptor. Then the J-20 performed a low-altitude pass and Cobra maneuver, a dramatic demonstration where the aircraft rapidly pitches its nose up to extreme angles. And something happened that Chinese officials did not want. The aircraft emitted thick black smoke visible to thousands of spectators and cameras documenting every moment. The smoke plume trailing behind China's premier stealth fighter became instant social media content, spawning analysis videos, expert commentary, and widespread mockery of what was supposed to be an impressive display of Chinese aerospace capability. The black smoke was not just aesthetically embarrassing, it revealed fundamental engine problems that exposed the J-20's limitations. Thick black smoke indicates incomplete fuel combustion, a hallmark of outdated engine technology. Specifically, it is characteristic of the Russian-derived AL-31 engines that still power early J-20 batches, 1980s technology that China has been unable to fully replace despite years of attempting to develop domestic alternatives. For a stealth fighter, producing visible smoke plumes is catastrophic. The entire purpose of stealth aircraft is remaining undetected. Black smoke turns the aircraft into a visible beacon that radar systems can track, infrared sensors can detect from enormous distances, and even visual observers can spot. The J-20's Zhuhai performance did not demonstrate advanced capability. It exposed that China's premier stealth fighter has a fatal flaw that undermines its entire operational concept. Today, we are going to examine what the Zhuhai incident revealed about J-20's engine problems, why the aircraft's design compromises stealth for other capabilities, and what this means for China's claims about having a genuine fifth-generation fighter. By the end, you will understand why over 300 J-20 aircraft might look impressive as a number but represent a deeply flawed aircraft that cannot match American fifth-generation fighters in the ways that actually matter. Let us start with the engine problem, because this is fundamental to everything else wrong with the J-20. The J-20 fleet is what analysts call a logistical Frankenstein, divided into three incompatible engine generations that create maintenance nightmares and operational complications. Batch 1 J-20s use Russian AL-31 engines, essentially 1980s technology that China purchased because domestic alternatives were not ready. Batch 2 uses China's domestic WS-10C engines, an improvement, but still not meeting fifth-generation requirements. Batch 3 is supposed to use the long-promised WS-15 engine that would finally give the J-20 genuine fifth-generation performance, except the WS-15 faces mass production failures and remains unavailable for most aircraft. This creates a configuration control nightmare. Parts cannot be swapped across variants, maintenance procedures differ, and training requirements vary. What should be a unified fleet of 300 aircraft is actually three fragile subfleets competing for resources, each with different capabilities and limitations. Logistics personnel managing J-20 operations must track which aircraft have which engines, maintain separate supply chains, and ensure crews are qualified for the specific variant they are operating. The AL-31 engines that produce the black smoke at Zhuhai are particularly problematic. These engines cannot provide the thrust necessary for super cruise, sustained supersonic flight without afterburners. This is a defining capability of fifth-generation fighters like the F-22, which can cruise at supersonic speeds while maintaining relatively low fuel consumption and infrared signature. Without supercruise, J-20 fighters must use afterburners to match American fighter speeds. Afterburners consume enormous amounts of fuel and produce massive infrared plumes, heat signatures visible to infrared sensors at hundreds of kilometers. The F-35 electro-optical targeting system can detect afterburner plumes from beyond 100 kilometers, giving American pilots awareness of J-20 locations long before those fighters can employ their weapons effectively. The WS-15 engine was supposed to solve these problems. China has been developing WS-15 for years, promising it would finally give the J-20 thrust and efficiency matching the F-22 F-119 engines. But according to reports, WS-15 development has suffered catastrophic failures. China cannot reliably manufacture single crystal turbine blades, the advanced metallurgy required for high-performance jet engines. Test engines have experienced explosions. Mass production remains elusive. Even if WS-15 eventually enters production successfully, hundreds of existing J-20 fighters will continue operating with the inferior engines for years. Retrofitting aircraft with new engines is expensive and time-consuming. The mixed fleet problem will not disappear quickly, even under best-case scenarios for WS-15 development. Now let's examine the design compromises that undermine the J-20's stealth characteristics, because engines are not the only problem. The J-20 features large canards, forward control surfaces ahead of the main wings. These canards were added to compensate for weak engine thrust, providing additional lift and maneuverability that underpowered engines could not deliver through pure thrust. Aerodynamically, canards work. But for stealth aircraft, they are disastrous. Canards deflect radar waves in unpredictable ways. When the J-20 maneuvers and the canards adjust, they create radar cross-section spikes that make the aircraft far more visible. Radar cross-section analysis suggests the J-20's frontal radar cross-section might reach -4 decibels per square meter at certain angles, compared to the F-35's -12 decibels per square meter. That is a massive difference in detectability. The F-35 appears orders of magnitude smaller on radar than the J-20. The J-20 also has exposed engine nozzles without the serrated shrouding found on American stealth fighters. The F-22 and F-35 use carefully designed nozzle treatments that reduce radar reflections from the rear. The J-20's exposed nozzles create strong radar returns from rear aspects, making the aircraft highly visible to adversaries positioned behind it during maneuvers. During the Cobra maneuver at Zhuhai, the J-20 wobbled and relied on canards for forced turns rather than demonstrating smooth thrust vectoring control. The F-22, performing similar maneuvers, shows stable, controlled movement through pure engine thrust vectoring without dramatic control surface deflections. The J-20 wobbling exposed poor super maneuverability and energy management, the aircraft fighting its own aerodynamics rather than flowing through the maneuver naturally. Visible quality issues compound these design problems. Observers note misaligned panels and visible rivets on J-20 airframes. For stealth aircraft, manufacturing tolerances must be maintained at micron-level precision. Gaps, misalignments, and surface irregularities break the stealth envelope by creating additional radar reflection points. The visible quality issues on J-20 airframes suggest manufacturing processes do not consistently meet the exacting standards that stealth aircraft require. In 2018, an incident showed that the J-20 stealth limitations are not just theoretical, because there is real evidence of the aircraft being detected by older radar systems. Indian Sukhoi Su-30 MKIA fighters tracked J-20 aircraft over Tibet using fourth-generation Russian radars. This was confirmed by Indian Air Chief Marshal Barinder Singh Dhanoa, who publicly stated that Su-30 MKIA radars detected J-20 aircraft from significant distances. If 1990s-era Russian radar aboard fourth-generation fighters can track J-20 aircraft, what does that say about the aircraft's stealth effectiveness against modern United States radars specifically designed to detect stealth aircraft? The J-20 was designed to counter the F-22 and the F-35, aircraft with far more sophisticated sensors than Su-30 Mk-1 radars. If the J-20 cannot avoid detection by older Russian systems, it certainly cannot avoid detection by cutting-edge American sensors, radars, and infrared tracking systems that benefit from decades more development and combat refinement. This real-world detection undermines Chinese claims about J-20 stealth effectiveness. Stealth is not binary. It is about reducing detection range and probability. The J-20 may have a lower radar cross-section than conventional fighters, but it is not low enough to avoid detection by modern systems at operationally relevant ranges. And when detected, all the other limitations, weak engines, limited maneuverability, design compromises become critically important. Now let's examine the J-20's weapons and tactics. Limitations because the aircraft's design reveals specific operational concepts and vulnerabilities. The J-20 lacks an internal cannon. This design choice reflects Chinese doctrine. The aircraft is optimized for beyond visual range combat, intended to engage American support assets like tankers and AWACS using long-range PL-15 missiles while avoiding close-range dogfights with American fighters. This doctrine has logic. Destroying force multipliers like tankers and AWACS could severely degrade American operational capability. But it also reveals Chinese assessment that the J-20 cannot win dogfights against F-22s or F-35s. The aircraft is designed to avoid close combat because it would lose in merged scenarios where superior American maneuverability, thrust-to-weight ratio, and pilot skill dominate. Without an internal gun and with limited close combat maneuverability, J-20s that are forced into visual range engagements have no options for fallback weapons or tactics. If long-range missiles are defeated through electronic warfare, chaff, or evasive maneuvers, J-20 pilots have no options for prosecuting targets. This makes the aircraft critically dependent on everything working perfectly: missiles functioning as advertised, sensors providing accurate targeting data, and adversaries not employing effective countermeasures. Professional military forces train for scenarios where nothing works perfectly. Equipment fails, communications get disrupted, and plans change rapidly. Aircraft designed with no backup options for when primary systems fail are vulnerable to the chaos that characterizes real combat operations. Let's talk about avionics and sensor fusion, because even the best hardware is useless without software that works effectively. According to analysts, the J-20 avionics rely on designs copied from United States F-22 and F-35 aircraft obtained through cyber espionage. China accessed design documents, specifications, and technical details through extensive hacking campaigns. But having stolen blueprints does not mean Chinese engineers can implement the systems as effectively as the American originals. The J-20 reportedly suffers from immature sensor fusion, the integration of data from multiple sensors into a coherent tactical picture that pilots can quickly understand and act on. American fighters automate this process extensively. The F-35 processes data from its own sensors plus data-linked information from other platforms, filters it through sophisticated algorithms, and presents pilots with a clear tactical picture showing threats, opportunities, and recommended actions. J-20 sensor fusion is reportedly less mature, forcing pilots into more manual data correlation. When multiple sensors provide conflicting or overlapping information, pilots must mentally sort through it while simultaneously flying high-performance aircraft in complex, tactical environments. This creates information overload that degrades decision-making exactly when split-second choices matter most. American fighter software benefits from over 20 years of combat data from Iraq, Afghanistan, Syria, and countless other operations. Threat libraries, electronic warfare profiles, and tactical algorithms are refined through actual combat experience against real adversaries employing real countermeasures. The software knows what to expect because it has been tested extensively under operational conditions. J-20 software is simulation-based with no real combat validation. Simulations are valuable but cannot replicate every variable, unexpected contingency, and chaotic condition that characterizes actual warfare. Software that performs flawlessly in controlled testing often fails when exposed to the unpredictable nature of combat, where adversaries deliberately do unexpected things to create confusion. This experience gap matters enormously. When J-20 aircraft face chaotic combat environments where communications are jammed, sensors provide conflicting data, and adversaries employ unexpected tactics, will the software and pilots handle it effectively? Or will the lack of combat-tested systems and procedures lead to confusion, poor decisions, and mission failure? Now let us examine what U.S. military leaders actually think about the J-20, because their assessments reflect professional judgment informed by classified intelligence. U.S. Air Force leaders like General Charles Q. Brown dismiss the J-20 as a pacing threat, not a peer. A pacing threat means something that influences planning and drives certain capability development, but it does not represent an equivalent competitor, an adversary with genuinely equivalent or superior capabilities that could dominate in direct confrontation. This assessment reflects confidence that American fifth-generation fighters maintain decisive advantages despite J-20 numbers. The U.S. is already developing sixth-generation capabilities through programs like Next-Generation Air Dominance, focused on maintaining air superiority against future threats. American planning is not centered on desperately trying to match the J-20 capabilities. It is focused on ensuring American fighters remain generations ahead regardless of what China fields. This confidence comes from understanding the J-20's fundamental limitations, the engine problems, stealth compromises, untested systems, and lack of combat validation that no amount of production quantity can overcome. 300 flawed aircraft do not equal a capability advantage over smaller numbers of genuinely superior platforms operated by experienced forces. The Zhuhai incident, where the J-20 emitted black smoke, was not an isolated embarrassment. It was a visible manifestation of deeper problems that plagued the entire program. The smoke, the wobbling during maneuvers, and the reliance on canards rather than pure thrust are all symptoms of rushed development that prioritized quantity and propaganda over solving fundamental technical challenges. That said, accuracy requires acknowledging China's real achievements. This does not mean the J-20 is useless, or that China has made no progress in aerospace technology. Building any stealth fighter is a genuine achievement. The J-20 shows China can design, manufacture, and operate complex military aircraft at scale. That matters. This also does not mean the J-20 poses no threat in any scenario. Against less sophisticated adversaries without advanced sensors or in specific tactical situations, J-20s could be effective. The issue is performance against peer adversaries like U.S. forces employing cutting-edge capabilities and tactics. This also does not mean China will not eventually overcome current limitations. Given enough time, investment, and development, China could solve engine problems, improve stealth characteristics, refine software, and build genuine fifth-generation capability. The question is timeline, and whether current aircraft represent credible capability or propaganda-driven production. But it does mean the J-20 is currently fielded has fundamental flaws that prevent it from matching American fifth-generation fighters in ways that matter operationally. The engine problems are not minor inconveniences. They are capability limiters that affect everything from range to detectability to maneuverability. The stealth compromises are not theoretical concerns. They are real vulnerabilities proven by detection from radars from the 1990s. So what is the bottom line on the J-20, and what did the Zhuhai incident reveal? China has produced over 300 J-20 Mighty Dragon stealth fighters and promotes them as peer competitors to American F-22s and F-35s. State media presents the J-20 as proof China has achieved aerospace parity with the United States. At the November 2025 Zhuhai Airshow, during what should have been an impressive demonstration, a J-20 emitted thick black smoke during maneuvers, revealing engine inefficiencies from outdated Russian-derived technology that still powers many aircraft. The smoke was not a minor aesthetic problem. It was a visible symptom of fundamental limitations. The J-20 fleet is divided into 3 incompatible engine variants, creating logistical chaos. Early aircraft used 1980s Russian engines. Newer variants use Chinese engines that still do not provide 5th-generation performance. The promised WS-15 engine that would finally deliver required capabilities faces mass production failures and catastrophic test explosions. Design compromises for stealth are severe. Canards added to compensate for weak thrust create radar cross-section spikes. Exposed engine nozzles make the aircraft visible from rear aspects. Visible quality issues suggest manufacturing does not meet the precision standards stealth requires. Real-world detection by Indian Su-30 MKI fighters using 1990s Russian radars proves the J-20's stealth is inadequate against even older sensors, let alone cutting-edge American systems. The aircraft lacks an internal cannon, betting everything on beyond visual range combat because it cannot win dogfights. Software relies on stolen designs but lacks combat validation and mature sensor fusion. U.S. Air Force leaders dismiss the J-20 as a pacing threat, not a peer. That assessment influences planning, but it does not imply equivalent capability. American focus on 6th-generation development reflects confidence that J-20 numbers do not translate to a capability advantage. The black smoke at Zhuhai was not an isolated embarrassment, it was a public manifestation of deeper problems. China prioritized quantity and propaganda over solving fundamental technical challenges. 300 flawed aircraft do not equal the capability that smaller numbers of genuinely superior platforms provide. The J-20 demonstrates China can build impressive-looking hardware at scale. Whether it can build hardware that actually works as claimed against peer adversaries remains unproven, and the evidence suggests significant gaps between appearance and operational reality. Don't forget to subscribe for more analysis separating military propaganda from combat capability. Thanks for watching.